Okay, section 2.5. This is theorem 2.5.6. Now we're skipping Cramer's rule. They just do it for the 2 by 2 case. Cramer's rule is a very neat rule about inverses of matrices. I actually used it once in trying to do a proof. For the most part, I've never really used it, but it's more of a theory tool than a numerical tool. But at any rate, let's go on to 2.5.6, and it says, let A be square and non-singular. Okay, if that's the case, then the homogeneous equation get that whole word in there. The homogeneous well, I really messed that up, didn't I? Try that again. Woo, a lot of extra letters. The homogeneous, much better. The homogeneous system, AX equals 0, only has the trivial solution. And so, again, that's the whole uniqueness thing and so forth, right? Proof, you simply start with your AX equals 0, multiply both sides by A inverse. And you get that X, oops, oh, I keep forgetting to write down A inverse there. A inverse 0, X equals 0. So it's just the trivial case. Okay, so that's good to know. And let's see. Do we want to do anything more with that? Yeah, I guess. Okay, we'll go ahead and add in remark 2.5.4, and it says that if A dot 1, A dot 2 up to A dot n are the columns of A, then okay, and this remark actually kind of points out that they are using their x vector in all these things as just a column vector, so I'm going to add my lines over that x. But then AX equal x1 times A dot 1 plus x2 A dot 2 plus all the way to xn A dot n. So again, this is back with the matrix multiplication. One way to view matrix multiplication is that the result of doing this is just taking a linear combination of the columns of A, okay, where the multipliers are just the entries in that x vector. And so if when you do that, you get the if we set it equal to 0, so what they're saying is consequently an implication of theorem 2.5.6, so our theorem that we just had here, is that if x equal our x1, x2, x3, xn here, if x exists such that x is not equal to the 0 vector, so not all of those xi are 0, at least one of them is non-zero, okay, exists such that the x are not 0, and ax equals 0, or another way to write it is back here with the linear combination, or x1 a dot 1 plus x2 a dot 2, okay, all the way up to our xn a dot n is, and that's a 0 vector, is equal to the 0 vector, then A is singular. Okay, it doesn't have an inverse. And in that case, what we say is the columns of A are linearly dependent. So this text, throws a lot of vocabulary in as remarks and so forth. So let's just make sure we have that linear dependent vectors. Okay, they're a set of vectors, and usually let's use v's, set of vectors, v1, v2 up to vn. Now this corresponds to the columns of that A matrix. A set V is linearly dependent if there exists constants C1, C2, Cn, not all 0. Now some of them could be, but not all 0, such that C1 V1 plus C2V2 plus CNVN is equal to the 0 vector. Okay, so that's linearly dependent, and then the set V1, V2, and so forth up to Vn is linearly independent. So linearly independent if C1 V1 plus C2 V2 plus Cn Vn equals 0 vector implies C1 equals C2 equals all the way up to Cn equals 0. Okay, and so that's what we're seeing with this theorem here, is that if AX equals the 0 vector implies the only answer is x equals 0, then A is non-singular and its columns are linearly independent. However, if there is a non-zero solution, okay, so if I can solve this such that the x isn't 0, if there's a non-zero solution to that, then A is singular and the columns of A are linearly dependent. Okay, so those are the implications they're making out of theorem 2.5.6. Okay.